Every
Recording in progress. 뭐라고?
녹화한 건데 녹화한 거.
아, 그냥 제가 그냥 얘기를 해주는 거구나.
스피커가 지금 항상 막.
우리 저거 막 그 돌아다니는 기계 있지 않나? 여기 어디 보면 저기 몇 개 있을 텐데 어딘가 회의실이나
있어야 됩니다. 원래 그
안 돼도 그치?
회의실에 있긴 했었어요.
그 이거
아니 저쪽 그 세미나실도 있지
네,
않나?
그럴 수 있습니다.
뭐 이거 바꿔볼까? 근데 이거 막 갈아 끼우면 되잖아.
네.
녹화도 할 때 그럼 지직되면서 녹화되는
근데
거예요?
지난주에 그 동주거 올라온 거는 문제는 없긴 없던데.
지금 스피커만.
그러니까 내 생각에 들어가는 건 괜찮은데
네네네.
오늘 거기 황 박사님한테 한번 말 한번 해보라고 해볼래요?
어,
일단 원래는 그냥 현재처럼 진행하긴 했었습니다. 한 몇 주 동안.
예스. 네, 문제 없네.
Hello everyone, I'm Hyunji from Biomarkers. So today's title is Insulin Resistance Prediction from Wearables and Routine Blood Biomarkers. So let's read the abstract and find the gap sentence first.
줌 탭으로 들어.
Did you find? Tell me if you find gap sentence.
How?
Yes, right. I think gap sentence says this. So diagnostic method for insulin resistance, it still remains expensive and inaccessible. So it can hinder early intervention of diabetes. So there are two types of diabetes. So the pathogenesis for type 1 is autoimmune disease. So it meant to attack pancreatic cells itself. And then for type 2, it's more like lifestyle, like obesity, physical inactivity, and genetic factors. From this, the primary cause of type 1 is impaired insulin secretion. For type 2 is insulin resistance. So insulin resistance is a key precursor to type 2 diabetes. For now, 537.
What is insulin resistance?
Um,
Impaired insulin secretion means cannot release the insulin. I guess.
yes,
What is insulin resistance? What is the difference from
like it doesn't work like for the insulin. It means so the insulin cannot work like as an insulin.
Oh, I see. So it releases something.
Yeah, it releases, but the glucose doesn't work by the insulin.
Okay.
So for now, 537 million people living with diabetes worldwide, and it is projected to reach 643 million by 2030. And here, IR, which is insulin resistance, it usually came from obesity, and obesity came from lifestyle. And those IR finally goes to type 2 diabetes. There are around 80% prevalence of IR among patients with type 2 diabetes. Of course, there are some methods for assessing insulin resistance, but there are some obvious limitations. This is the gold standard for assessing insulin resistance, but it is limited because we have to go to research facilities and it's expensive and really time-consuming method. And there's another assessment, we call this HOMA-IR. But in this formula, we need fasting insulin and fasting glucose. So actually, it has the same problem with the gold standard, which is we have to go to the medical facility, even though it is more affordable and faster than the gold standard way. So this shows why we need to and why we have to use the wearable data for assessing insulin resistance. So
Can you explain the gold standard formula one more time? What is fasting insulin times fasting glucose?
fasting insulin and fasting glucose is in Korean like 공복혈당. So we have to do the blood test. So that's why we have to go to the hospital. So they said this is the limitation of that assessment because really we have to go to the center.
So higher insulin, higher glucose are bad,
Yes.
according to this formula. And really, does it make sense why high insulin, high glucose both are bad? What that means? 한국어로 얘기해도 되고 영어로 해도 되고. 네.
그 인슐린 저항성이 세포가 인슐린에 반응을 안 하는 거거든요.
그치.
네, 공복에 인슐린이 많이 나온다는 거는 세포가 얘를 인슐린을 어떻게 보면 디텍트를 한다라는 의미로 볼 수 있고,
그치.
인슐린이 높은데도 글루코스가 높다는 거니까.
그러니까
또 반응을 안 한다는 또 그런 거죠.
그러니까 우리는 글루코스를 낮춰야 되는데, 왜냐면 인슐린을 원래 주면 글루코스가 내려가야 되는데, 이놈의 세포가 반응을 안 하니까 계속 인슐린은 처음에 10 줬다가 반응 안 하면 20 주고, 20 줬는데도 반응 안 하면 30 주고, 그러니까 인슐린은 계속 끊임없이 올라가는데, 글루코스는 안 내려가요. 그래서 두 개 팩터가 둘 다 높으면 문제가 있는 것이죠. 그러니까 예를 들어서 왜 둘 다 필요하냐면 인슐린이 적은데, 글루코스는 높은데 인슐린은 적어. 그 얘기는 이거는 타입 2가 아니라 어떤 뜻이지? 타입 1이란 거지. 인슐린이 릴리스가 안 돼서 글루코스가 안 내려가. 그래서 글루코스가 안 내려가는 원인이 두 종류가 있는 것이지. 인슐린이 맞아서 그러면 인슐린 나가게 만들면 돼요. 그래서 그건 이제 팬크리아만 고치면 되는 건데 우리 몸의 세포가 인슐린에 반응을 안 한다는 건 어떻게 보면 더 어려운 문제일 수도 있습니다. 그러니까 한 대 때렸을 때 일 잘하는 애가 그 다음부터는 2대 때려야 되고 3대 때려야 되고 이렇게 되는 거예요. 그래서 타입 2가 조금 더 몸 전체를 고쳐야 되는 거니까. 진짜?
So some researchers did the research about the wearables and insulin resistance, but previous studies were limited to association analysis between wearable signals and IR. So that's why we need the prediction model.
Can you explain the graph?
And this is the top 3 features of wearable highly correlated with HOMA-IR, which is the authors did in the paper. So RHR and daily step count and HRV was the best features of wearables with IR.
Sorry, I don't get that correct. Can you explain? What is x-axis, y-axis?
So on the right side of the x-axis, it means IR. So
Impaired IS, impaired ISIR.
yes, IS means insulin sensitive, which is we can call this normal. And the impaired IS is like middle of the IS and IR. And then we can say that
The y-axis.
RHR means the heart rate during the rest. So if the heart rate during the rest, if high, it means more like the IR status.
그래서 이제 봐봐. 오늘 요가 첫 번째 프레젠테이션이니까 뭘 고쳐야 되냐면 우리는 과학을 연구를 하는 사람이잖아. 그럼 어떤 결론을 얘기할 때는 자정이 있어야 되거든. 근데 갑자기 그래프를 보여준 다음에 그냥 결론만 얘기하면 사람들은 청주는 너를 못 믿게 된다. 이제 학교에 가서 발표. 뭔가 숨기는 게 있나? 그래서 그래프를 띄웠으면 가장 기본은 X축이 뭐고 Y축은 뭐고 그래서 이 그래프가 의미하는 건 뭐라서 그래서 이게 돼야 되는데 그냥 끝에 것만 얘기하면 교회온 거랑 똑같아. 우리는 과학을 해야 되는 거니까 종교가 아니라. 오케이? 다시 한번 이 그래프가 떴다고 생각하고 모든 그래프는 X축, Y축 관계 그리고 거기서 우리가 할 수 있는 이야기는 이거다. 오케이? 근데 이게 생각보다 쉽지 않아. 다시 한번 해볼까?
So this graph shows the x-axis means the level of IR and y-axis is the feature level of the wearable devices. So it shows the correlation between the wearable data and the human IR. So like this, the previous studies were usually limited to association analysis, like the correlation between wearable signals and IR. So here we can know that we need the prediction model.
Okay. You didn't explain what is exactly x-axis and what is exactly y-axis.
X-axis is the level of the IR. So the IR means the high insulin resistance, and IS means insulin sensitive. So it's kind of normal status. And y-axis it's the value of each wearable data.
What is that?
So first one is RHR. It means the heart rate during rest.
Exactly. So think about it, Hyunji. When you across this hole and just grab the random person, do you know what is RHR? What is the chance they know what it is? RHR. Did you know it? No, right? That means you have to explain it. So, example. So, and everyone, this is very important. When you give a talk at a certain place, I know you know what is IR, impaired IS, RH now, you know it, but these people, they don't know. So then, when you show this, here is a normal person, resistance person, this is a middle person, and y-axis is heart rate at the rest state. But you can see that as resistance becomes stronger, heart rate at the rest state becomes slightly higher and higher, increasing, right? But look at the variance. What do you think? From if you give a heart rate at the rest value, can you distinguish these three classes or not? What is the chance? Right? I know there is slight mean differences, but variance is so high. Are they statistically significantly different or not? Not at all. So we cannot use this value to distinguish these three states, unfortunately. Although this is top one among the wearable data. And then this is top two, right? So top two is daily step count. That means when they become resistance, they move less. It makes sense, right? Usually IR come from the bad people. Those people don't walk less. So trend is good. But the problem is again,
Variance.
large variances. So if we bring this, can we distinguish? No. Again, same issue. What about this? Heart rate variability. So as the resistance becomes stronger, heart rate variability becomes lower and lower. But again, mean difference is this much, but variance is huge. So there is a trend, but unfortunately useless. That's the point. 이렇게 하면 설명을 이 그래프 3개에 대해서 제대로 한 거야. 어떤 컴포넌트가 있냐? X축이 뭐였고 Y축 뭐였는지 설명했지. 그리고 이 안에 있는 그래프 내용을 다 설명했어. 트렌드도 있고, 근데 이게 있어. 그래서 결론은 뭐다? 이제 그 얘기를 할 수 있어. 저 위에 있는 거. 뭔가 링크는 돼 있는데 그걸로 가지고 예측할 수는 없다. 그래, 저 얘기를 하고 싶은 건 알겠는데 그걸 하려면 스텝 바이 스텝으로 가줘야 사람들은 이해를 했다고 생각합니다. 이해됐나?
네.
그래서 모든 그래프를 어떻게 설명한다? X축, Y축, 그 다음 그 안에 있는 이거를 설명하기. 왜 본인 논문 쓸 때 이 그래프 하나 그릴 때 한 3분이면 그리니? 아니면 하루 종일 가지고 이거 그렸어? 하루 종일 잡고 그리지. 그 메시지를 전달하려고. 그럼 그 그래프 상대방이 하루 종일 그린 그래프를 설명하려면 적어도 2, 3분은 써줘야 예의가 아닐까? 오케이? 네. 보시죠. 자, 오늘은 제가 계속 좀 인터럽션 할 겁니다. 오늘 정현재 학생의 첫 프레젠테이션이어서 유만 그런 게 아니라 여기 있는 모든 선배들도 첫 발표 때는 계속 내가 태클 하면서 가르치니까 정상이야. 태클이 없었던 사람이 미나였나?
아니요.
완벽해가지고.
아니요.
미나 완벽해서 태클이 없었던.
마우스.
그치? 한 박사도 없었지 전혀. 완벽했어.
아니요, 그렇지 않습니다.
농주 완벽했었나? 그러니까 정상이야.
And this is a whole modeling pipeline for HOMA-IR prediction and LLM-based interpretation, which was proposed by the authors. So for the input, they use several data like wearable data, demographic, and blood biomarkers, and some health information. And for ground truth, they use HOMA-IR, and the cutoff was 2.9. And for output, they use IR levels. So actually, there were 3 levels as IS, impaired IS, IR we saw before, but the authors made it by 2, so IR or not. So finally, they solved this problem as a binary classification. So also, they wondered which combination of data best explains insulin resistance. They had wearable, demographic, and biomarker data. So they wondered which data combination is the best. And especially for the wearable data, they wondered how we have to process it. So for processing wearable signals, first they use aggregation method. So like statistical summary, like mean, standard deviation, and median. And they also tested for aggregation window with 7 days, 14 days, 30, and 60. And through these tests, they found the 7 days was the best aggregation window. And to find the best data combination, they use XGBoost model with the task 25 feature combination with those data, like just wearable and wearable demographic and wearable and biomarker, something like this. And there are several categories of biomarker. So finally, they could make the 25 combinations. And they also compared the 3 modeling approaches of XGBoost learners. First is L1, L2 learner, which is linear learner. So this is the loss function. And the first term is the prediction error. And the second term is L1 penalty. So it makes some coefficients go to 0. And third term is L2 penalty. So it suppresses some coefficients to go too large. And the second is tree learner, which is nonlinear learner of decision tree. So the first sigma term is prediction error, and the second one is about also penalty. And third method, they use combination with
What kind of penalty? Tree penalty. Can you explain TK and omega K? Why we want to use it?
The TK, the penalty for TK means they suppresses the huge number of leaves of each tree. So it suppresses to be not to be like so complicated. And the third one is also work like L2 penalty. So it regulates the each prediction vector of in each tree. And then the third one is the combination with mask autoencoder and L1, L2 learner. So first they pass the original input variables through the mask autoencoder with the masking probability 0.75. So they use the value G as their input value X. So they got the value like Y hat here. So they use the same loss function with the first one, the L1, L2 learner.
Can I have some question?
형준아, 미안한데 질문하면 안 돼. 여기 스피커 고장 나가지고 질문하고 싶으면 채팅창에다가 적어주면 미나가 읽어줄 거란다.
기다리다 넘어갈까요?
기다려. 그러면 우리 기다리는 동안 what about this simple thing? Anyway, the goal of these two are same. We want to make the coefficient of this beta j is not that large. What is the difference between L1 and L2 and why they do both? Doesn't it look redundant? Anyway, minimizing the absolute value of the beta j, minimizing the square. What's the difference? Why they do this? 생각해볼까? 뭐 어쨌든 쟤들 둘 다 크게 만드는 건데 왜 저렇게 쓰잘데기 없이 두 개를 다 하고 있을까? 컴퓨터 힘들게. 그렇잖아요? 얘도 베타가 너무 크면 페널티를 주고 얘도 베타가 너무 크면 페널티를 주죠. 좀 어쨌든 베타가 너무 크게 안 만드는 건데 얘와 얘 왜 둘 다 쓸까? 이상한 놈이네. 생각해 볼 사람? Why? 이런 페널티, L2 페널티 뭐가 다를까? 뭐가 해볼까요? 우리 학부인 현중에 한번 얘기해볼까? 이거 틀려도 됩니다. 정답이 있는 건 아니라서. 군인이 해볼까? 어떨 것 같아? 절대값을 낮춘다는 거랑 스퀘어를 낮춘다는 거. What is the difference between? Yeah.
첫 번째, 한국말로
당연히.
에러 페널티는 어쨌든 저 L을 지금 베타로 미분을 해서 최소화를 할 건데 에러 페널티를 베타로 미분을 하면 베타가 크든 작든 기울기가 1이라서 똑같은 속도로 줄어드는데 에러 페널티는 큰 게 더 많이 줄어듭니다.
그렇죠. 좋습니다. 아주 좋은 스트레이트인데 얘는 어떤 느낌이냐고 그래서 얘는 적당히 작게 만드는 게 목표인데 얘는 어떻게 하든 0을 만드는 게 목표. 방금 좋은 포인트 미분을 하면 0까지는 그냥 0이었는데 이게 이렇게 올라간단 말이죠. 그래서 the goal of this is actually we really want to make the goal of LNOM is minimize non-negative value. Minimize the number of the non-negative value. That's the goal. This one is small values are okay. It doesn't need to be zero. Okay. The goal of this is maximizing the number of the zero values. This is 0.01, we don't care. As long as small, we are fine. But both are, sometimes people only use this. Sometimes people only use this, sometimes they use both. But in this case, they use both. 형준이 채팅 도착했어?
네.
읽어주십시오.
What is the aggregation window and how do they select the best window?
네. Aggregation window가 뭔가?
It means we have to select the window for process the wearable signals. So 7 means they for the aggregation, the mean or standard deviation, they selected the 7 days and calculate the mean for the 7 days, something like this.
Everyone understand? Yeah.
And like the way they choose the best window, I think the performance of XGBoost model. So based on that model, they choose the best window.
7 had the best performance.
Yes.
So yeah, just think about it. They will represent just one value from that aggregation window, like your activity count, for instance. So we will measure your activity count every day, like for a month. So there are several ways. For a month, you average out to one number. For 7 days, you average out one number. Then every 7 days, we will get a one number. What is the best? I think, of course, small window is always, I guess, better because we don't lose any information. But what is the problem of using a small window? Then there are too many pictures. It's a high dimension data. So that's always pros and cons. So if we have a small window as an aggregation, then we don't lose the information. The best thing is, why don't we do every day? Every day step count can be pictured. So for instance, Mina, for your one month available data, if we use a 1 day window, your step count will become 30 dimension vector. But if we use the 30 days aggregation window, then it will become just one number. Simple, complex, and of course complex, don't lose any information, but then you need a GPU. Yeah, that's always pros and cons, but that's why they choose the 7 was best, and why they didn't try
Less than 7.
Yeah. 3, that's my natural guess. We wanted this kind of things. But anyway, they choose 7 days. But it's possible that, let's think about it. So they say it's 30 days, but 14 days, 7 day accuracy is increasing, right? Correct? That's why they choose the 7 day as best. But in 4 day, maybe it could decreasing. Why? Although it is more detailed info. Isn't it special number for us? 7 day means?
It contains weekend.
Yeah, 1 week. Kind of, if you use the 4 days, only if you're Monday to the Thursday, Wednesday to the Sunday, your activity count, same or different? Monday to the Friday, your activity count is nearly 0, isn't it? So what about weekend? Yeah, so depending on that choice, it could fluctuating a lot. So that means the 4 day window could be misleading, isn't it? Correct. So that 7 day could be very natural window for choice. So yeah, that's why they choose the 7 and then 14 and then some 30 and 60. Good.
So with this XGBoost regression model with those learner, they got the higher value and they just did the classified it. It's higher than 2.9 or not. And this is the result. And the x-axis means the R squared and y-axis show the combination of the data. So as you can see on the bottom, the best combination of data was wearable, demographic, and some biomarker data like lipid panels and metabolic panels. And for this case, the best option for learners was mask autoencoder plus L1 and L2 learners.
So, what is a lipid panel and metabolic panel? Is it some blood info?
Yes, so there are some categories of the blood biomarkers.
So, and to get the lipid panel and metabolic panel, we need to do blood tests.
Yes.
And we are set, isn't it? The goal of this study is not to do.
Yes. But finally, they found this combination was the best, and they more focused on the processing way for wearable data in the later parts.
But this lipid panel and metabolic panel are different from that gold standard fasting glucose test. It's different.
I think it's the same way because in their data they did the blood test on the really start from the research period.
약간 헷갈리는데 이 연구의 목적이 뭐지? 피를 안 뽑고 뭘 하겠다는 거 아니었나? 그 피 뽑은 정보를 이용해버리면 그냥 그걸 하면 되는 거 아니야?
I think they wanted to make their like the foundation model in first, and then they validated it on another data set.
일단은 약간의 우리 모두 의심을 가지고 시작을 해봅시다. 지금 약간 이상하죠? 오늘 흐름이. 일단 the easiest thing is wearable plus demographic. So that one is around 0.2, 3 R square. In the middle there are
The wearable plus
Yeah.
demographic around 0.2.
Yeah. So let's do step by step. Wearable, yeah, lowest. So we expected, right? At the first graph show is just wearable feature, it doesn't work. Demographic, your age, height, is it? And gender is better than your smartwatch. But actually, important conclusion. There is a hidden message. Your demo. So, actually, believe or not, a lot of this digital health study, beating the demographic information is usually doesn't work. Your demographic, your age, most important information. You cannot beat Apple Watch, Google Watch, PP, Galaxy Watch. No. Your age, gender, nationality, that's the most important information, unfortunately. So this is very normal, okay? And then sometimes when you merge it, usually here, it doesn't change. Like listen, the sleep foundation model. Demographic information, they use the whole PSG and wearable, blah, blah. Same. Doesn't change. But when they add, although it looks small, it's quite good in my eye. Because these two adding become this. Look at it. This info, definitely have their own information. That's very good news. But if you add this to the location of this is exactly the same with this. What that means? Wearable info is just demographic info, useless. So this is also very, I think this is an important conclusion to understand the insulin resistance, not only your age and gender, it's wearable and it provides some info. I think that's very important conclusion here. And then this one, fasting glucose. This is one of the gold standard info, right? Sure. They are here. 0.3. This is sort of the gold standard, sort of. Then, I don't know how much difficult to get this lipid panel. If we combine these three, same. And it also has some meaning. Oh. But I don't know how difficult this lipid panel and metabolic. Can you search what is lipid panel? 뭐라고? lipid panel 뭐를? 콜레스테롤 검사나? 그치. 이게 내가 이거 뭐냐? 패스팅 글루코스보다 얻기 쉬운 건 잠깐 물어볼까? 그러면 인정. 아니 얘는 매우 어려운데 얘는 좀 쉬운 거면 인정해도 되겠다. 어? 인간에서 얘는 굶어야 되고 얘는 안 굶어도 된대요. 큰 차이가 있네. 그러니까 피를 뽑는데 얘는 그냥 뽑으면 되는 거고 얘는 금식을 좀 많이 해야 되는 거다.
음식을 논패스팅으로도 가능한 거예요.
아, 저 리피드. 네, 오케이. 그러면 여기 조금 더 인정, 그렇지? 그러니까 어떻게 보면 얘가 벤치마크 좀 되는 게 아닐까? 그러니까 병원에서 쓰는 게 이 정도. 그럼 얘를 이기는 거면 당연히 좋은 거고, 근데 우리의 제일 관심사였던 이게 제일 쉬운 거잖아요, 그렇지? 얘랑 좀 할만한 거 아닌가? 병원 가서 힘들게 한 거랑 많이 발전했네요, 그죠?
그냥 뽑아서 할 수 있는 거 병원 아까도 된다는 거.
그래서 글루코스 왠지 내 생각에는 이 콜레스테롤 이걸 왠지 뭔가 쉽게 할 수 있는 장치도 있지 않을까라는 생각. 뭔가 집에서. 모르겠네. 일단 적어도
글루코스가 혹시 CGM이?
아니요. 이건 그 CGM으로 사실 할 수도 있지. 근데 여기서는 CGM은 아니고 그냥 병원에서 되는.
CGM 된다고.
굳이 이걸 할 필요는 없긴 해. CGM은 비쌌고. 네, 아시죠?
Yes, so the key is multimodal data integration and mask autoencoder. So then how can you upgrade this MA further? So they use a pre-trained MA-based wearable foundation model to predict homo-IR. So they use LSM2 style WFM pre-training, and they had two types of masking, inherited and artificial mask. So inherited mask means the natural missing values. So they didn't do any pre-processing for that missing value. They just used that as a mask. And then artificial mask is what we know for the artificially we make the value as the masking value. And then they input the initial cohort into the WFM encoder. Here they use 26 sensor signals from wearable data, and total signals has 3,744 tokens per day. And also they added the positioner embedding about what time of day and which of the 26 signals. So through this, we can get a wearable embedding for 1 day. And to get the whole total N days wearable embedding, they use median pooling of daily embeddings into a unified individual representation. So here we can get a wearable embedding for one person about the N total day.
이거 처음부터 다시 해주십시오. 어렵습니다. 다시 1번부터 WFM이 뭔지 한번 설명해 주시고.
WFM means the wearable foundation model. So they use the pre-trained foundation model. So the key feature of the model is that they has two types of masking. So actually there was a version 1 about the LSM. for that, they pre-processed the missing values and they use it as an input value. But here, the feature is that they have two types of masking, inherited and artificial mask. So inherited mask means the natural missing values. So they didn't do any pre-processing for the missing value. And then artificial mask is what we know about the artificial mask for the encoder. And then they use the model, the LSM two style foundation model, and they put their own data, the cohort data, to that encoder. So when we pass the 26 sensor signals to the WFM encoder, they can get a wearable embedding for 1 day. And then to get the whole total N days, they use that median pooling of each daily embeddings into a unified whole total embedding. So finally, in this process, they can get a wearable embedding for 1 person about the whole N total day.
Okay, good. So very good. So 여기서도 one more lesson. So everyone, when you write the paper, when you give a talk, most important don't forget is old and new. What is old and new? 현준이 박사님, old and new가 뭐죠? 우리가 뭔 얘기를 할 때 그냥 얘기하면 안 되고 어떻게 해야 된다? 그 전에 거랑 연결해서 무조건 해야 한다. 안 그러면 인간의 뇌는 갑자기 새로운 정보가 들어오면 힘들어요. 여러분 앉아서 수업 듣는 거 좋아해요? 안 좋아해요? 미나 넌 좋아하는 거. 근데 대부분 안 좋아하죠. 듣는 거 안 좋아해요. 근데 새로운 정보가 들어오면 더 안 좋아. 그래서 봐봐. WFM이란 건 갑자기 새로 들어온 정보예요? 아니면 여기 있는 사람들 그냥 다 아는 상식이야? 다 아니 이거 뭔지? 보통 모르는 게 정답 맞지. 근데 그러려면 새로운 걸 얘기할 때 뭘 해줘야 되냐면 그 전에 거랑 어떻게 연결이 될지 암시를 줘야 되는데 Let me show you example. So okay. So you said okay, anyway, wearable plus demographic is pretty good, but still not enough. But when we develop this wearable data, what kind of feature we use? We bring the wearable data and then just we calculate the mean, median, standard deviation to simplify the time series data to the feature, right? Basically, we did an embedding, right? Low dimension embedding. How? Whole 1 week time series data to the mean, median, standard deviation. So we reduced this whole long time series data to the how many dimension? 3 dimension times 24 feature. So that much is our vector, right? But is it best? Yeah, it's a natural choice. It's easiest choice. I know it's easiest choice, but is it best? So the other wonder, this is really best embedding or not, so that they decide to use wearable foundation model as another way for embedding. 자, 이렇게 하면 기존이랑 지금이랑 연결되나요? 안 되나요? 되죠. 그래서 이거는 평생 여러분들이 까먹으면 안 돼요. 태근 이번에 글 쓰면서 제일 혼난 게 뭐였지? 이거지. 그냥 모든 사람은 앞에 거 생각 안 하고 두 번째 달라 그냥 글 쓰기 시작하고. 근데 이거 쉬운 스킬 아니야. 그래서 이 연습을 계속 해야 합니다. 자, 그러면 what the World Foundation model is developed by the Google. So basically what they do is they will make this low dimension space. How they develop this low dimension space is they put a huge wearable data set. When that data set will make the masking, will remove the data. And that the goal of this low embedding is if we reduce to this dimension, and then when we do the decoding, this masked part should be recovered well. So when we can recover the missing part, when? Only when the low dimensional structures are well maintained, then we can recover the original structure, isn't it? So that's why they use masking. That means this low dimension space should be pretty good. So if mean, median, standard deviations are well, then if we use that picture, this masking should be recovered, but of course, this should be better. So then what they did is, again, we use exactly same 20 sensor signal. Here, you don't need any like a window choice. We don't need it. Just plug in this data to that WFM. Then every day they will get some embedding. Then what they did is, of course, they can use whole this as a one-person picture, but rather than this, they will just median. Then for one person, we will have this one low dimension space. So difference is we use this WFM, but previously this component was like a mean of the step count, mean of my heart rate of variability, mean of something. So very simple picture. But now this is very nonlinear embedding result. So the key difference is previously we use a simple mean, median, standard deviation, but here we use autoencoder or decoder type nonlinear dimension embedding. 자, 이렇게 하면 제가 계속 새로운 얘기를 할 때 뭐랑 계속 같이 얘기해요? 올드랑 뉴랑 섞어서 얘기해주면 사람이 마음이 편안합니다. 오케이? 됐나? 자, 그러면 오늘 2개 배웠다. 그래프 읽는 거랑 올젠유. 이거 2개 하면 논문도 잘 쓸 수 있어. 그게 전부거든. 과연 근데 구글에 웨어러블 파운데이션 모델의 효과가 어느 정도 될까? 대충 아까 0.2 얼마였던 것 같은데 그래서 0.2 얼마면 좀 슬플 것 같긴 한데 혹시나.
And then they selected the top 5 principal components via PCA. So finally, those 5 features of wearable with demographic and blood biomarker data, they put those data to the IR classification process. So this is the whole process for a wearable foundation model. Here, they use 2 cohorts.
But they again use this not only the wearable demographic, they use this glucose and lipid.
No, they just use this for wearable data.
Just for the PCA part, can you go back? But they will use fasting glucose and lipid.
So the PC is just for the wearable.
Wearable, right?
Yes. So they selected 5 wearable features, and then demographic and blood biomarker data combined together and put the classifier.
So they didn't use the wearable plus demographic combination.
They use.
They will do all combinations.
Yes.
Okay, good.
So for this model, they use 2 cohorts data. So the objective of the first initial cohort is for model training and internal tests, and they did the external validation on the independent validation cohort. So this is the number of the participants of each cohort, and they use Fitbit as their wearable device. And the number of participants per each IR group was not that imbalanced. So this is the result of each cohort. So on the left side, we can see the metric with AURC and specificity, sensitivity, because this is based on the classification problem. And the row means the combination of the data. So the very bottom data is data combination is what we know the best combination, the demographic and wearable and two lipid panel and metabolic panel. And right on the right side, we can also see the similar or the same results. So the best combination here, we can know the wearable data, which was derived from the wearable foundation model, not just aggregation, with the demographic and biomarker data.
근데 우리 궁금한 건 그거지 않을까? 그래서 WFM 써서 우리가 할 수 있는 건 테크닉입니다. WFM 써서 얼마나 증가했는지 한번 같이 디스커션 해주면 현지가 좋겠다. 한번 비교해볼까?
So,
그냥 우리 기존에 미디안 썼을 때에 비해서 팬시한 오토인코더 썼을 때 얼마나 좋아졌는지 볼까?
So on the right graph, the orange color bar is the aggregation wearable data, and the purple one is the WFM style wearable data. So as you can see here, in all that case, the WFM was better than the aggregation method, but especially for the data combination with the demographics and the blood biomarkers with the WFM style wearable was the best. The ARC was 0.88 in this case.
Oh, that's nice. So what do you think, everyone? The same wearable data, when they use the foundation model, you like it? Or this paper published by Google Group? Or
Some of,
some of them are Google.
yes.
Okay.
But actually, the authors, the LSM to foundation model also worked this paper.
오케이. 다른 안으로 볼 수 있지만 그래도 이 정도면 훌륭하지 않나? 그러니까 얘 demographic and wearable인데 근데 우리 aggregation 했을 때는 차이가 없는데 이게 우리한테 주는 메시지는 뭘까? 자, 여기 지금 수많은 웨어러블 하는 분들이 있을 텐데 우리 그냥 어떻게 보면 우리는 이제까지 요 방식 쓰지 않았나? 그러니까 우리 파운데이션 모델을 쓰고 있는 사람 있나? 웨어러블 하는 친구들 중에?
이제 막 시작하려고 하거든요. 팩트 쓰고.
그치. 여기 하나 쓰는 게 이쪽. 현 박사님 쪽이 요거 쓰려는 거지. 근데 구글 파운데이션 모델이 아니라 다른 파운데이션 모델 쓰.
네, 그렇습니다.
오,
수학생 왔어야 되는데.
무슨 요리요?
소위
예비군 갔어?
네.
강민이랑 같이 갔니?
예.
아니, 그러니까 강민이 예비군 거 아니면 원래 같은 날이야? 이런 예비군.
잘 모르겠어요. 생 예비군 수학관.
그렇구나. 고생하네. 그러니까 승훈이가 유튜브 찍으니까 들으려고.
네, 한번 먹으라고 해야 돼.
근데 일단 이거는 약간 팔이 안으로 공부 쓸 수도 있는 페이퍼긴 합니다만 일단 이게 우리한테 주는 메시지는 한 번쯤은 해봄직한 거 아닌가? 우리 동주? 박사? Your mood disorder prediction. Are you belong to this orange class or purple class? Because we only use mean, median, standard deviation. 그치? 월드 파운데이션 모델에다가 웨어러 파운데이션 모델에다가 인베딩하면 더 좋아질까? 너무 안 해보고 싶나? 한번 무드 했었잖아요. 이거 어베일러블 한 건가? WFM?
데이터는 이제 어그리게이션 된 것만 제공을 하고 있고, 그 요청을 해야 또 얻을 수 있고.
아니, 구글에서 제공하는 이거 프리트레인된 이 파운데이션 모델 인베딩 하는데 우리 거 하려면 이 거 쓸 수 있는 거 공개돼 있나요?
이 페이퍼들 그 코드 공개돼 있긴 한데 완전 풀리는 아닌 것 같고 조금 수정하는 절차가
그치. 구글에서 만약에 공개해줬으면 이거 다운받아서 그냥 로우 디멘전 인베딩 할 때만 쓰면 돼요. 그 우리 데이터. 뭐래? 네.
다들 다 보여줬어.
그렇긴 하지. 그래서 공개되어 있으면 근데 만약 우리의 희망은 이런 거 만약 우리 연구실의 목적은 이런 거 하면 재밌지 않을까? 우리는 저거 플러스 모델링 추가할 수 있잖아, 그치? 우리 모델링이 구글 보다 더 좋으면 어떡하지? 그러니까 우리 슬립 프레셔랑 서케이디언 리듬 우리 자체로 에스티메이션한 정보가 저 월드 파운데이션 모델을 인베딩 시킨 것보다 더 좋으면 구를 갈 수 있다. 바로.
질문.
음.
WFM을 쓴 게 밸리데이션 한 거보다 다른 거다 근데 스페시피시티는 낮거나 아니면 거의 효과가
하다.
떨어져.
문제가 될 수도 있죠.
언급하진 않는데 너무.
그냥 뭐만 증가한 거야? 그러니까 스페시피시티는 똑같고
ROC 기준으로.
내려가기로
그렇죠. 센시티비티가 올라간 건가? 그래서 퍼포먼스가 좋아지는 거? 그렇지 않은데. 맞네. 그러니까 여기는 임프루브가 없고 센시티비티만 올라가면서 ROC가 올라가는데 그게 뜻하는 게 뭘까? 스페시피시티는 그대로인데 센시티비티가 올라갔다는 건 뭐를 더 잘 디텍트해낸 걸까? 의미가 뭐야? 나 맨날 헷갈려. 스페시피시티는 그대로인데 센시티비티만 증가했다. 이게 뭘 뜻하는 걸까?
아닌 걸 아니라고 얘기해.
응.
센시티비티는 맞는 걸 맞는 거.
그렇지. 그러니까 그러니까 정상인 사람을 정상이라고 얘기하는 거는 별 차이가 없었는데 질환이 있는 사람을 있다라고 하는 게 더 좋아졌다는 뜻이니까 이게 뭘 뜻하는 걸까? 그러니까 정상인 인간들은 이 파운데이션 모델로 인베딩을 하나 평균값을 쓰나 거기서 거긴가 봐. 근데 이 질환이 있는 분들은 평균값을 보는 것보다는 뭔가 이 복잡한 인베딩을 했을 때 뭔가 시그널이 잡히나 보네. 그 정도 메시지는 있을 수 있겠네요. 사실 디스커션에는 이런 내용은 언급했으면 좋았을 법한 내용이긴 하지 사실. 좀 저자들이 게으르고 구글이라 그런가 봐.
그리고 한 가지 제가 궁금한 점이 이 기존에 했던 웨어러블 데이터, 그러니까 지금 이 모형을 학습한 웨어러블 데이터에 미싱이 얼마나 있냐, 그죠?
그 LS2,
아니.
LS2 스타일.
지금 글루코스, 이 논문 자체에서 하고 있는
그러니까 이 웨어러블 데이터의 미싱이 좀 그러니까 퍼센트가 얼마 될지 잘 모르겠는데
그래서 그 절차를 다 해서 마지막으로 남은 게 보면은 처음에 4,000명 모았는데 그런 전처리를 다 해서 남은 게 1,100.
그 미싱이 없다고 봐요.
저 안에는 이제 마지막으로 모아둔 거 안에는 없다.
미싱 아예 없는 상황이에요.
알 수 없지.
근데
쓸 수가 없을 텐데.
근데 LSM2 스타일을 쓴 거 자체가 이제 그 미싱 밸류를 전처리하지 않겠다라는 전제인 거니까 아무래도 있긴
그죠.
있었을 것
이
같은데
미싱 밸류를 처리한 게 혹시나 저
그게
개선의 핵심이니까
재밌네. 근데 일단 뭐 좋은 건 구글에서 저 사실 파운데이션 모델 만들 때 몇 년 걸려서 만든 거긴 하거든요. 왜냐하면 트레이닝 데이터가 엄청난 트레이닝 데이터를 해서 만들어 놓은 파운데이션 모델인데 그게 나름 쓸모가 있다는 걸 너무나 보여주고 싶었겠지. 그래서 그 의도가 반영된 논문이어서 아마 하일리 셀렉티브된 페이퍼일 수도 있으나 그래도 가능성이 있어 보이잖아요. 그럼 우리 웨어러블 하시는 분들은 안 할 이유는 없다. 1번. 두 번째는 얘들보다 우리 방식을 썼을 때 더 잘 되는 걸 보여주면 내 개인적으로는 더 기쁘겠다. 두 방향으로 한번 다 생각해 보셔도 그래서 해서 나쁠 건 없을까. 그러니까 어떻게 요약하고 싶냐면 얘들은 에그리게이션이랑 그 두 개를 비교하고 있는 거잖아, 그치? 근데 거기 우리가 할 수 있는 건 콤비네이션 더 넣는 거거든요. 얘들은 이 두 가지만 비교하고 있는 거야. 근데 악사가 했던 건 사실은 이거라고 맞나? 악사랑 동주가 한 건 이 방식이지. 그치? 근데 걔들이 이거는 보였어. 얘는 어디에 속할까? 얘보다 낫겠지? 얘랑 비등할까? 질까? 이길까? 그게 내 첫 번째 질문. 이거 하면 얘 이길 수 있을까? 응. 그래서 얘의 위치가 부등식에서 어디 있는지가 매우 저는 사실 개인적으로 궁금하긴 합니다. 어머, 프로젝트다. 할 수 있지. 애그리게이션 할 수 있고 모델링 다 해놨잖아요. WFM으로 인베딩만 시켜서 그 피처만 더 추가해서 저 부등식에서 저 어디 돌아갈지 만 생각해내면 돼요. 그러면 우리가 이기면 어떡하지, 구글? 괜찮을까? 얘들 기분 상하지 않겠지? 보자. 재밌을 것 같아요. 그래서 어, 오, 일단 근데 WFM이 효과적이라는 걸 본 건 전 처음이라서 왜냐면 WFM이 나온 지 1년인가밖에 안 됐어요. 근데 공개가 되는지 모르겠어. 그거가 되는지 체크를 해보고.
And they didn't stop just prediction. They also made an LLM-based IR agent, which can interpret prediction and provide personalized recommendations. So it was powered by Gemini. And this IR agent needs two types of input. The first one is user's question, and second is personal health data. So this is the example of the response of IR agent. So this agent interpret the result of the prediction, and they provide some recommendations. So here they use their trained IR ML models as their agent toolbox. So of course they did the evaluation of these IR agents. So the first objective of the agent's evaluation is adding IR prediction information to an LLM improve its responses. And the second one is, are the IR agent responses factually accurate and clinically safe? So for this, they selected 5 participants' data with atypical metabolic profiles. Also, they recruited 5 doctors, the endocrinologists. With them, they did side-by-side comparison between their base LLM Gemini versus their IR agent. So this is the result. On the left graph is the result of side-by-side comparison. So they didn't know the answer of the IR agent or the Gemini, and they selected which one is the better. So for the all factors like comprehensiveness, trustworthiness, personalization, the IR agent was better than the base LLM. And they also did the absolute evaluation of their agent. The accuracy of factuality, safety, and citations was good, but the accuracy of reference and interpretation was not good, like under the 50%. And here the limitation of here is, especially for the blood biomarkers, interpretation was low. So this is their IR agent limitation. Yes, so this is all today, and the summary first, the wearable foundation model derived wearable representations captured richer physiological patterns, and the data combinations with wearable and demographic and blood biomarker achieved robust IR prediction with an around AURC of 0.8. And also they made LLM-based IR agent, which can do the personalized interpretation and guidance. Thank you for listening.
네.